We have four speakers today. Our first speaker is Derek Mendez. Derek is a computational project scientist at both Lawrence Berkeley Lab as SLAC National Lab. His work involves developing novel every pixel analysis method. And today we're going to talk about ExaFEL. So please, Derek.
All right. Can you all hear me okay, I guess? Okay, great. See some thumbs up. Hi, I'm Derek. I work at SLAC now officially, and I'm an affiliate at Berkeley Lab where I used to work. And I'm going to be talking about exascale computing and trying to encourage everyone to use supercomputers and to get a supercomputing pipeline set up. And just thanks to the organizers for inviting me. Now, what you see here on this slide is the Frontier supercomputer. Someone's wiring up these servers. And this was the first exascale supercomputer in the United States. And it's one of the, if not the fastest computer in the world right now. There might be a few computers in China that are also exascale that are not being reported. But anyway, so what is exascale? What does that mean? I was trying to look up for things that number in the exascale, and I found a curious fact that there's 0.02 quintillion ants on Earth. So that's 20 times 10 to the 15 ants, which is a lot of ants. If you were to stretch them out along a line, that would be 40 trillion meters, which is further than the Earth to Pluto, actually. So I thought that was pretty interesting. And if you could hypothetically have an exascale population of ants, that would be on the scale of light years. So exa is a very large number. Oh, I'm gonna start my timer, by the way. It also happens to be the number of floating point operations that the Frontier supercomputer can operate at peak performance. So this would be using every single processor, in this case GPUs, simultaneously. And a floating point operation is, called a flop, and it's just, think of it as matrix multiplications and matrix vector multiplications, this kind of stuff. And I was curious what a human can do, and I found this interesting article last night. Seems about 3 flops is what the average, what a above average human can operate at. So computers can really help us out sometimes. So there's these big computers, and a big driver for the development of these computers are actually light sources. And so, there's this exascale compute project that's funded by the Department of Energy in the United States. And they have several goals, but one of them is light source enabled analysis of protein molecular structure and design. And there's several teams working on this, and these are just a few. And I was working with Nick Sauter and Michael Wall and Johannes at Berkeley. And so I'm going to be talking today about some of that work. But basically, light sources are going to be generating lots of data in the coming years. That data rate is going to increase dramatically. And so people need to figure out how to use these facilities to handle that data. And so that's what the exascale compute project is all about. And this is just a quick picture that I like. This actually wasn't obtained, I think, with a light source. And this is an illustration, obviously, but the interesting structural phenomenon is that there's these waters in this channel that are helping it to maintain its structure. And so this is kind of the interesting science that we want to elucidate with light sources. And one technique for getting at these details is crystallography. And today I'm going to be talking about serial crystallography exclusively. And so this is one of the first demonstrations of serial crystallography done at an XFEL at LCLS. And this was work by Henry Chapman. And you can see here you have crystals that are being injected into the path of this XFEL, and you measured diffraction, in this case on 2 detectors. The back detector is looking at kind of low resolution scattering. And so you look at many crystals and you can kind of merge the data from all the crystals. So in this case, 15,000 images were used to form this merged intensity to get the diffraction, the electron density of this photosystem molecule. And just this is an interesting example of the fact that you can do studies of very small crystals at an XFEL. So from this low resolution detector, they were able to get crystal size information, and they were looking at crystals as small as 200 nanometers, which is pretty interesting. Okay, so where do you do this kind of experiment? So this is done at free electron lasers. You can do serial crystallography also at synchrotrons, that we'll hear about more of that later. But this is Spring 8 facility, and you have the Spring 8 synchrotron there, and the line is the SLAC. And I'll be skipping over a few slides periodically because I think I have way too many. But just a quick overview of the differences between a synchrotron and an FEL. One of the main differences is the length of the undulators that are used to produce the radiation. So at a FEL, you have a very long undulator, which is used for the lasing process. And then you dump your electron bunches at the end of that lasing process. So if you look inside of an undulator, what's going on is at the start of the undulator, you have synchrotron radiation. And then that radiation acts on the electron bunches that emitted it. And this creates a feedback loop, which phase separates the electrons into micro bunches, each one at a slightly different wavelength. And it's a somewhat randomized process. And this is why you get that noisy, sassy spectrum. And this is called spontaneous, self-amplified spontaneous emission. And so when you're phase locked, you're kind of more coherent than you would be otherwise. So that's where you get the coherence from. So you get really bright pulses of X-rays at FELs, and these are the FELs in the world that are operational right now. And if you look at these columns, the properties like the range of energies, the photons per pulse, these are all roughly the same scale, but there's some outliers here in the pulses per second column. So LCLS-II is a currently in development extension of the LCLS, and it's going to be operating at a megahertz or up to a megahertz repetition rate. And European XFEL is here at, you can on the order of 10,000 pulses per second. And so why are there these outliers? And if you go back and look upstream of the undulator at the actual accelerator technology that's used to get the electrons to very high speeds, you'll see that at the European XFEL and the LCLS-II, they're using superconducting technology, which means you can operate at a really high duty cycle, high rep rate, without destroying the instrument, because the copper would otherwise get too hot from resistance. Okay, so this is technology used in flash, and also going to be used for the International Linear Collider project, I believe. Okay, so quickly now, I'll just show this picture of LCLS-II. You can see those superconducting cavities there at the bottom. And the undulator is just over here. All right, so LCLS-II is initially going to be just soft X-ray, but it's going to have a megahertz rep rate, and you're going to be able to kind of use whichever pulses you want, is kind of what they're saying. And however, that's, soft X-ray is obviously not too interesting for crystallography. I found this stat in a paper somewhere, just from someone who queried the PDB, most crystallography experiments, like I think 99% of them happen in this energy range shown in orange. But there is, because of this, there is a planned high energy upgrade to the LCLS-II. Maybe, I don't know when, it was supposed to be online already, I think, but so maybe 3-5 years after LCLS-II is accepting proposals, then you can expect to be able to do crystallography at the megahertz. Okay, and then why would you ever do that? So we heard a great talk yesterday afternoon about time-resolved crystallography, so I don't think I need to say too much. These are just several examples of systems that are quite involved and just showing that there's interesting biology happening at all timescales that you could imagine. So, when you have a megahertz crystallography and you're getting up to 1 million images a second, you can imagine being able to really study dynamics systematically. Instead of going to the XFEL and getting 1 or 2, 3 time points in 2 days, you might end up with orders of magnitude more. So this, I think, will be really helpful for time resolved. But there's other kinds of experiments that you can imagine that would benefit from having high throughput. And so this is recent work that's showing here you have hybrid materials that form these really tiny crystals. And you can study them at XFELs to get their structures. But they produce these really sparse diffraction patterns where they're really hard to handle. And there's usually when you have a limited number of spots, you try to index these images and you get a large kind of error on your orientation matrix. And it's hard to refine that orientation matrix because you have such limited data. And so really you need to take a lot of measurements. And so this would also help these kinds of screening experiments. Okay, so this was published in 2015, just showing a lot of motivation for what you would do at LCLS-II. So if you're interested, even though it's a little bit old at this point, I think there's a lot of interesting stuff in here. However, if you want to do high rep rate crystallography, you can already at the European XFEL. And so this diagram shown here is a typical setup for doing high rep rate crystallography at the EU XFEL. And I'll kind of go through this kind of loaded slide in steps. So the first thing that you see at the bottom here is the pulse structure. So at the European XFEL, you actually get 10 pulses a second. But if you zoom in on one of these pulses, you see a sub-pulse structure. This is called the pulse train. So each one of these pulses actually is made up of 1,000, order 1,000 smaller pulses, or sorry, called sub-pulses or something. I don't know what to call them. But and so each one of these you can actually use to do an experiment. And people have been studying this and studying whether there's any kind of systematic errors if you try to use pulses that are just neighboring, because these are separated by 900 nanoseconds. There's been time-resolved studies where they'll use the first pulse in the pulse train to look at a dark state, and then they'll excite their sample with a laser and then look at subsequent pulses to kind of do some kind of time resolved studies. So you can read about these. Now, if you're going to be using pulses that are spaced by 900 nanoseconds, you have to think about injection and getting your crystals in there and getting them out of there as fast as possible. And so in order to do this, one of the currently best ways to do this is using a GDVN, which you can see here, which uses helium gas to focus a stream of your crystals. And these can go fast, up to 100 meters per second. If you go too slow, so when you run faster, you make your beam also thinner, which is also good, as you'll see in a second. This is what happens if you run too slow. And so you can see here that the first pulse is causing the jet of your crystals to fray, and then by the time the second pulse arrives, it hasn't recovered yet. And so, this would basically be a very bad data set, because all this spray would show up on the detector and it would just look very speckly and bad. But if you run up to 100 meters per second here, you can see that by the time each new pulse comes along, the jet has recovered. And so when you start to plan for these megahertz experiments, you really have to think about injection and how you're going to do that. Okay, and then there's the star of the show is the camera. This is the adaptive game detector that they have at the European XFEL. And it's really kind of the limiting factor because you can really actually only read out 3.5 kilohertz, even though you have 10 times as many pulses. So right now the detector technology is limiting the throughput, but that's still a very high number of diffraction images a second. And this paper came out, this kind of data deposit of 19 million images that were collected in 90 minutes at the European XFEL. And so that's a lot of data. You get very fast. And you can process this offline and it's not a big deal. 19 million images in a data set is kind of typical for an XFEL experiment. However, in 90 minutes, if you wanted any kind of real-time feedback, which is, if you've been part of an XFEL proposal and experiment before, you know that people, users really want to know, have I got enough sample to move on to my next sample, right? And how do you process this amount of data in 90 minutes? And you can read about this on European XFEL website, or just do the math. If you collect for a few days, you might get a petabyte of data, and that's not uncommon. Remember, this is 3.5 kilohertz. The full throughput is 10 times faster, and then LCLS-II might be even more. So each one of these chips can be read out here at looks like 3.7 gigabit per second if you're at full throughput. So you can imagine, I don't actually know the details of the readout system, but maybe each one of these is on a different Ethernet cable going to a different file. But all in all, there's 16 panels here, so you're looking at about 50 gigabits per second, which is a high number. And this is the 1M. They're planning a bigger detector as well that has, I think, 40 or something of these chips. Okay, so there's lots of data that needs to be processed quick. And I'm going to skip through these slides, but this is basically what needs to happen to every image if you want to have some kind of, when you do analysis, and what you're going to need to do fast if you want real-time feedback. So, we saw this yesterday as well, but this is the typical pipeline for doing SFX analysis and serial crystallography. So you have to detect the strong spots and index the pattern, predict scattering from some basic models, do an integration, and kind of tally everything up. So that's all the per shot analysis that gets merged into your structure factor intensity solution, which you can then feed to your favorite program to get your structure solution. So how long does all this take in practice? I have another data set that I was looking at from SwissFEL. This is Jungfrau 16M data. Large area detector data. And I just wanted to see how fast can I process on NERSC, which is a supercomputer at Lawrence Berkeley National Lab. But to be modest, I used 4 compute nodes, which totals about 160 processors. So probably everyone here has access to this kind of computing. And I clocked in at a rate of 78.7 images per second. And this is kind of the breakdown. It's not too important, but this is the breakdown of what each step was doing. So I was actually reading from disk, but 78, so let's say I was at 100 images per second. I'm still falling short of 3.5 kilohertz. So at this rate, if I wanted to look at those 19 million images, it's going to take me 67 hours. And so I can't, using this kind of computing setup, I cannot get the feedback to the users in time. But because I'm on the supercomputer, I simply just increase my number of nodes. This, of course, would have to be reserved ahead of time. But what's interesting is that supercomputing facilities want you to do this. So that's what I'm going to talk about next. So how can you leverage supercomputers? So I found this report that just came out of Berkeley Lab, and basically all these authors here want you to use supercomputers to do your science. So the first letter of the abstract here is the superfacility model is designed to leverage HPC for experimental science. Okay, so if you're gonna use a supercomputer to do your work, how do you get you have to get your data there. And so this is kind of the first step. And this has been known, and this energy science network was planned in the 80s. And you can see here, these are just fiber optic cables that are running all throughout the US and actually over to Europe as well. Some of them are up to 400 gigabit per second, right? So you could easily handle a European XFEL experiment currently in this network if you have the cabling hooked up. But I know there's people that want to make this happen. And the work I'm going to talk about next, we've done a test run of this whole setup. So we were just using this small section here from SLAC to NERSC. And I believe it's 200 gigabit per second, dedicated fiber optic. So this is the work of Johannes that I'm going to talk about next. We did a trial run of the superfacility model for serial. So what that means is for two user experiments, we did it for 2 experiments. We wanted to see, can we provide adequate feedback, and is the pipeline scalable? Let's see here. We used just 64 compute nodes. Each computer has 32 processors, so 64 times 32 total processors to do the analysis. But this is actually not, this is kind of small compared to the state of the art. So we used this Corey Haswell partition at NERSC, which in total is 2 petaflops. Remember, we're already at an exaflop with Frontier, so 3 orders of magnitude lower here. And then we actually only used 2% of that system. So we were using roughly 50 teraflops peak performance. Okay, and this is LCLS-I, so it's 120 hertz. So this is what the superfacility API looks like. You collect your data at your light source, you pipe it over to your superfacility using the ESNet. You process your data there, and then you report back to a database that your users can then probe using any application that they write or that you write for them. So basically, this database will store things like run X has this many indexed images, so something like this, kind of lightweight stuff. And then the users, you might have some application that's plotting indexed images versus time or something, and the users can look at this and see if they're that's what's happening over here. But the point is that all of this has to be scalable if you're going to meet the high data rate demand. And and what that means is it needs to operate on many compute nodes every step of the way. So transferring data, you have to use multiple computers at your light source and at your destination. You need to utilize all of this. When you run your jobs, you also are using multiple computers. And when you have this database that holds all your information your users are looking at, this has to be very stable. It has to be secure, but it also has to be fault tolerant, and it has to be on all the time. All of this kind of stuff requires many applications running that can run on multiple computers as well. And so that's what Spin is doing is Spin is using something called Kubernetes under the hood, which is kind of an orchestration management software. So basically everything's scalable and multi-computer, and it's kind of already done if you can find out how to use these tools. So I'll just quickly talk about the data transfer. I honestly don't know too much about this, but this was born from particle physics, where they have lots of data. They also generate lots of data at these particle colliders. And the root software, if some of you might have heard, kind of is underlying, I think, a lot of the particle physics software. Root is something object-oriented. Couldn't find the acronym, but I think it's supposed to be the root from which all the particle physics development happens. But basically, they need to provide data to users fast. And so from this are these protocols like xroot dcopy, which are used to deliver data using multiple computers very fast. And so this was basically set up to automatically transfer our data to LCLS using multiple computers on either side of that transfer. Okay, so then once your data are at your super facility, you need to process them. And we use MPI to manage the fact that we're using multiple computers to process our data. And so MPI will launch a root process, which we feed into the root process the raw data instructions file. And this just says, for example, shot A is in file X on server, whatever, so that the root can then distribute work to workers. And so this is sometimes called the master worker or root worker. There's all kinds of names for this paradigm. But basically the workers, when they then process an image and then they ask for another one from the root, and then the root hands them out. I work with Art Lubimov, and he calls it the mama bird, baby bird approach, which I thought was pretty funny. So once these workers exist on any number of computers or compute nodes, they write their data and then they commit messages to the database. Okay. So when you're running this big application, there's certain kinds of diagnostic tools that you'll want to use. So this is called a time diagram, and you can see that on the y-axis you have different worker IDs, and there's a color code for what they're doing at any given time. And if you just look at this, you see there's a lot of white, which is MPI comms, and that's actually not supposed to be happening. And so once that was fixed, in this particular example, there was another issue happening here. You can see all this blue. Blue's indexing, and why are some workers taking so long and getting stuck in the indexing? There was some, file system error happening because the indexing jobs were logging too much data to the disk. And so supercomputers are great, but they're not perfect. And so you have to kind of work out these kinks. But then once that was fixed and the logging was cleaned up, and then we got pretty nice performance here. This is, okay. And this is basically just an example of what's happening kind of in real time, is that you're collecting data. So those are the green blocks. And as soon as one run, data are organized into blocks called runs. As soon as one run is finished, it gets copied and you begin the real-time processing. But sometimes you're at the experiment and you realize, oh, I forgot to use a mask, or oh, the detector geometry is horrible, we have to reprocess the data. And so this happened occasionally where we have to start over, and then you get behind on the real-time processing. But eventually you catch back up. Okay, so yeah, I just want to say a couple more things here. There's fast computers out there, and how fast of a computer can you use? So at the European XFEL, I believe they have access to the Maxwell cluster, which is, I think, around 2 to 10 petaflops. I'm not sure at peak performance. And this is showing the list of the top 500 computers that are currently available for use. This gets updated periodically. Okay, last little section here, getting the most from your super facility. So you can see here, super facilities are really using GPU technology under the hood. And what that means is that if you really want to get up to the exascale, you should really think about writing algorithms on GPUs. And I have a few suggestions for that. If you go that route, you'll want to think about multiple architecture. So Frontier is using AMD GPUs, and Perlmutter at NERSC, which is the new system, is going to be using NVIDIA GPUs. And so there's ways that you can write one code for multiple architectures. So that's something to really think about here when you start developing for these things. Okay, and there's an archive paper if you want to read about this that shows that Cocos, which is a single, it's a single code for multiple architectures, how that can be used to simulate diffraction and how that scales on different systems, and it does well. Okay, so when you're getting lots of data really fast, you want to think about, do I need to save every shot? And how can you quickly figure out whether or not to save a shot? And so this was a paper that came out in 2018 from Nick Sauter's group, where they just trained a neural network to tell you, does my image have diffraction, usable diffraction? Okay, and we've kind of been doing that at where I work now. This is, I won't go into the details of this slide, but I work at SSRL mainly, and we have a sister beamline at LCLS. And so we've done some testing on serial crystallography at our beamline and kind of AI classification of images. And one of the good things about this is that when you have some kind of AI application, those can run on GPUs. And so this is the kind of thing that you can take advantage of at the supercomputer, where you have thousands and thousands of GPUs at your advantage. Okay, it's time. Okay, so I'll just say quickly that we're able to predict resolution from diffraction patterns that could then be used to kind of sort images and maybe process those images first. So I'm gonna skip to the, sorry, way too many slides. I'll skip to the end. Thank you very much. Use your supercomputers.